Hello everyone, welcome to this lecture 8 in the module Dielectric Properties of Insulator. And recall in the last lecture I have discussed how to distinguish between a microscopic or local field that acts on individual atoms, ions or dipole moments, and a macroscopic field which is felt by thousands of atoms, let's say, like an average over a long distance. And we discussed that how do you go from the microscopic field to the macroscopic world by doing some averaging technique, right? Similar question we can ask about this polarization vector for the material, right? Let's say we have a piece of solid, right, in 3 dimensions, and we know we have some primitive unit cell, right, inside the volume, and let's say it's the cubic cell, and then this is the primitive cell of some volume, and you can repeat this cubic cell and make the entire crystal, right? That's the idea. And every primitive unit cell, let's say, have some permanent electric dipole moment or some moment, right? That's the local field we are talking about. So P is the electric dipole moment in the volume element in the primitive unit cell, right? So, and then P is the macroscopic field per unit volume, right? The question is, how do you relate these two quantity? So this one is microscopic polarization, and this is macroscopic polarization per unit volume, right? So we can show using some averaging technique that the polarization, macroscopic polarization at some point R inside this piece of solid is nothing but the local field acting on a primitive unit cell divided by the volume of the unit cell. That's a formula to remember. So you can see, if you know the unit cell volume, which is known from the X-ray diffraction experiment, and then you can, if you try to estimate the local moment of the primitive unit cell, then you know the macroscopic polarization vector, right? But the question is, in the last lecture we have seen that the local polarization of the primitive cell, which acts on individual ions, atoms or the permanent dipole moments, is nothing but some polarizability of the material times the local electric field acting on that primitive unit cell, right? So that's why, in order to calculate the local polarization of the primitive cell, you need to know the electric field, the local electric field. That's the important thing to remember, that the local electric field is not the average electric field that applied in the sample. The question is, how do you find out this local electric field? That's the topic of discussion now. Usually this is due to the Lorentz technique, because Lorentz first show that how one can estimate this local electric field. To understand the idea, let's say we have a piece of solid, and inside that solid we have all those points, lattice points separated by some distances, and this separation is really small, in the order of angstrom ranges. And what you do, that let's say we have a very big sample, and this is some part of the sample, and then outside the sample we have some external sources where from which we can apply some electric field or something, right? We need some external sources. The idea is that, let's say we want to discuss what is the local electric field at some point R inside this solid, right? So the idea is that we want to divide the entire space into 2 regions. One is called the near region from this point, and one is called the far region from this point, right? And how do you do that? So the idea is, so that's a 3-dimensional picture. You have to understand that this is a 2-dimensional space, so I'm just you have to visualize the 3-dimensional sphere. So let's draw some sphere in the 3-dimensional space, right, of some radius. So the radius consists of, you can see 1, 2, 3, 4, 5, 6 lattice points, some 6 times some lattice point, right? So it's like some integer multiple times of the lattice distances. So any point that lies within this sphere of some radius is known as the near region for this point R. And any point outside this sphere for this point is known as the far region. Why? Because the idea is that if you place any charges in these points which are inside the sphere, they will affect the electric field at the position R like significantly. But if some point outside this sphere is far away from the point of interest, that's why if you put some charges there, their effect will be small, right? That's why we are dividing the space near and the far. And in the far region, we have some part of the sample, of course, and then we have all the world like external source and whatever, the experimental lab, whatever you can think of, right? So everything outside is in the far region. Now, the question is, how do you analyze this problem? To do that, let me introduce a number of electric field for this problem. The first one, so for every electric field, we will put two subscript, and we have to understand how to read this subscript. So number one, the superscript is micro, and the subscript is far, and then we have the argument R. That's number one, let's say. Then we have E. On the superscript, we have macro, and in the subscript, we have far, right? And we will explain what does this term really mean. So number three, let's say we have E local near R. And then we have something which is E near macro. How do you interpret these terms? So this is the electric field at a point R, right? Okay, electric field at a point R. What kind of field? It's a microscopic field. So microscopic electric field at a point, and the electric field must be some charge due to some charges, right? That's always the case. So we are saying this is the microscopic electric field at some point R for the charges that are in the far region. So we are considering this is the point of interest, but any charge outside this sphere will contribute some electric field right here, and we want to know what is that electric field due to some charges outside the sphere. The second one is the macroscopic field, right? So electric field, which is a macroscopic origin, macroscopic electric field at some point R due to the charges in the far region. So we need to perform some sort of averaging over this microscopic field to get the macroscopic, right? Then we have the local field. Electric local field means microscopic field due to the charges in the near region, right? That's why we have a near here. And the near region means any charge that you put on these points of the lattice points of the primitive unit cell, the effect of the electric field felt by locally at this point, right? And then we have the macroscopic field due to all of the charges inside this near field. They will create some electric field in this position R, right? So these are the different kind of electric field that we kind of thought of, right? So whenever you say far, it's like outside the sphere. When you say near, it's inside the sphere, and then you have to understand what kind of field we are talking about from the superscript. Is it a micro, or is it a macro, or is it something macro or local? So local is kind of micro, right? Okay. Now, you know the electric field at some point. Let's say we have two charges, and we are asking what is the electric field here. So you count the electric field due to this charge, and then from this charge and you superimpose, right? So electric field obeys the superposition principle. Now let's perform some sort of superposition principle in your analysis, right? So let's say we want to understand what is the electric field. So this is the electric field without any subscript. That's the standard that we have been using so far in your in other courses, right? And this is obviously the macroscopic field we are talking about, right? So when nobody really told you that that's a macroscopic electric field because it wasn't necessary there, but now we know it's kind of different from what we are discussing. So this macroscopic electric field at some point R, right? So there will be two contributions which will made up this macroscopic field. One is the charges due to the which lie in the near region, and one which lie in the far region, right? So this macroscopic electric field will have two components. One is the macroscopic, but in the near region, the charges are in the near region, and then we have something which is known as the macroscopic, but charges are in the far region, right? That's how you think about this term. Now, from this, you can see that the E far, so I want to write down the expression for E far macro, right, which is nothing but ER minus this term. So ER minus E macro near, right? That's an expression we will be using a bit later. So the far field, so the macroscopic field at some point R due to far charges are expressed by in terms of near charges and the total macroscopic field. Now let's analyze what about the local electric field at some point, right, R. Similarly, the local field will have two components, right? One for the charges inside the sphere which are near charges, and one for the far charges, right? So let's say we have two components, E local near at R and E local far at R, right? Now this local is micro, right? You have to understand that what I mean by this local charge means the microscopic electric field, right? So you can also write, instead of the micro you can write the local, you can write micro, right? They are the same. Now one thing, I will replace this microscopic field, right, for the far charges. Let me explain one thing. Let's say we are trying to calculate the macroscopic field, electric field at some point R, right? Macroscopic due to the far charges. And we know how to do the average from the previous class, right? The idea is that you need to do the average on the microscopic electric field due to far charges, right? Some points which is indexed by R prime, and you will weight that function with the weighting function, and then you will integrate over dr prime, right? That's how you perform the macroscopic from the microscopic electric field in the far region. The idea, you can see, what is this term? This is saying that this is microscopic field at some point R minus R hat due to the charges in the far region, right? But you know the effect of far region charges are really small. So this term, physically it means, let's some charges here. The effect of this charge on every point on this, on every point inside the sphere is kind of small, right? So we can see that every point will have experienced the same electric field due to this charge, because this is, let's say, far away point, and then its effect is almost the same in different points within this sphere. That's why you can see this term, this microscopic field, is sort of fixed or constant in different points within the sphere. That's why you can bring it out. This is independent of the points. And so when it is independent of the point, there is no meaning of shifting the function, because that's a single value at point R is any value within the sphere. That's why you can just bring it out, because it's a fixed number from the integration, and just write down R, right? And then we have left with the integration of the weighting function. And we know that from the property of weighting function, that's equal to 1. So you can see what that means is that the E macroscopic field for far charges is equal to E microscopic field for the far charges, right? And that's why you can see we have E microfar here. Instead of microfar, we can use macrofar. They are the same because the charge effect from the far field is very small. So let's replace this micro with this macro, right? So then we have this E local at some point R is E local near plus E far macro, right? And we know what is the E far macro from this expression, right? That's like E far macro. So let's put the value there. So we have E near local R plus this bit, right? Near macro. So ER minus macro near charges, right? So we need to find out the local electric field, we need to know these two things, right? One is the local charge at some point due to the near charges. Another one is the local charge or near microscopic charge due to the this is the macroscopic electric field due to the near charges, right? These two terms we need to find out. Let's say there are ways, in a separate lecture I will show you that why these two components, we know the value of these two components, right? The first one, the local electric field due to the near charge at some point R is 0. This is related with the symmetry of the crystal, and in the lectures to come I will explain how that can be shown, right? Let's say for this lecture we know that this is 0, and then we have the total macroscopic ER and then minus of this macroscopic field, right? Let me make it clear here. It's a macroscopic. This macroscopic thing, you can write it as the polarization, the macroscopic polarization PR minus and then 3 epsilon naught. And if you recall, this expression looks similar because I have introduced this term in the first lecture where I have shown that a sphere which is uniformly polarized, right? Which is uniformly polarized, that sphere, inside that sphere, any point inside that sphere has this amount of electric field, right? That PR by 3 epsilon naught. So this minus and minus get cancelled. So ER plus PR by 3 epsilon. And why we are using the expression for uniformly polarized charge, that I can say in here, because you can see what is this? This is the macroscopic electric field at some point due to near charges. So it is as though forget everything outside this sphere, only concentrate on the inside this sphere. So we are trying to understand what is the strength of the electric field, the macroscopic one, due to all the points here on which we have some charges, right? So let's say we have this, and the charges are distributed uniformly. And let's say the charge is such that we have some plus charges on the positive hemisphere and the northern hemisphere and some minus charges because these are dipoles, right? So every point consists of some dipoles, and then the negative hemisphere we have some negative charges, right? So that can be thought of as uniformly polarized sphere. That's why we are using this E macro near is nothing but the charges due to uniformly polarized sphere, right? That's why we replace this term. But why this term is 0, that requires a separate discussion, and I will bring that in the lectures to come, okay? So this is the expression for the local field. So why we are after that? Because we have the quantity that we want to calculate is the P, right? And we show that P is nothing but alpha times E local. Let's say this is the local electric field. Now we have the expression for the local electric field, and you can put the expression and then you can calculate the terms, right? So let's try to understand what this expression will give us. So what is the expression for the local field? Let me manipulate this term and show you that this will lead to a very important equation which is known as the Clausius and Mossot equation. So let me go to this page. So the idea is that we have this expression. So let me be consistent. So maybe I'm writing the local in subscript, sometimes in the superscript, but you understand that they are the same. So the local electric field is nothing but the total average electric field plus the polarization divided by 3 epsilon naught, right? And recall that what is the expression for the polarization for a linear dielectric material? Because this is linear material, the polarization goes as epsilon naught, which is the permittivity of the free space, times the electric susceptibility of the material, times the linear power, which is E of the electric field, right? And we also remember that 1 plus the susceptibility of the electrical susceptibility of the material is the dielectric constant or the relative permittivity, right? So from that we can see that susceptibility is nothing but dielectric constant minus 1. So let me put that expression here. Electric field, right? That's the condition for P. So if you put the value of P in this equation, and let's put P, right? So the E local at some point R is nothing but ER, then 1 by 3 epsilon and P, right? What is P? This is P. So P is epsilon R minus 1 times E, right? So this goes out and we have, if I take the epsilon R, we have this expression, and if you manipulate this, you can see this is nothing but electric field epsilon R plus 2 divided by 3, right? That's the expression for local electric field. So we know what is the expression for local electric field in terms of ER, and we also have this expression, right? So let me write down now the expression for, I think somewhere I have to make a correction, because this field is not the total polarization, right? You have to remember from the previous lecture, that's the microscopic. This is a local field. The local field is related with this polarizability with the microscopic field, right? So you can see that if you want to go to the total polarization vector, you have to divide it by the volume element, right? And so the expression will be, we'll have a volume element in the denominator, which is the volume element of the primitive cell. So that's the correction I need to make here. Now we know the expression for of this P in terms of E local, right? And what is the, we will put the values of E local and P, and then I will have the expression, right? Let's write the expression here. We have P, and then on the right hand side we have alpha by V E log, right? So what is the expression for P? We know this is epsilon naught epsilon R minus 1 times the electric field, right? That's for P. And what is the expression for E local? That's the expression for E local. So let's write it down. Epsilon R plus 2 by 3. And then you can see this E goes out. So we have regulation dielectric constant minus 1 divided by dielectric constant plus 2 from here. On the right hand side we have alpha 3 epsilon naught into the volume of the unit cell, and that's the famous Clausius-Mossotti equation for dielectric materials. That involves dielectric constant, because we know the relative permittivity is nothing but the dielectric constant. And if you look at the relation, one physical significance is that on the left hand side, dielectric constant, we have dielectric constant, right? And on the right hand side, we have alpha and V. The dielectric constant of material you can measure in the lab. That's a macroscopic quantity. But on the right hand side, the alpha is the polarizability of individual atom ions or the dipole moments, and V is the primitive cell volume, right? So this relation is kind of relating the macroscopic dielectric constant with the microscopic ingredients of the material, right? Because the volume unit of the primitive cell, that's like depends on the crystal structure, right? We have to know from the X-ray diffraction what kind of primitive cell you have. And this alpha is the polarization constant of the individual dipole moment, right? So these are really microscopic, but this is a macroscopic. So this relation is nice, that where you can kind of know one by knowing the macroscopic from the microscopic, right? That's the significance, and this is widely used in different standard literature. You will see this Clausius and Mossotti equation. And I think for this lecture, that's about it, and thanks for listening.